Hi everyone. Today we are going to look at sketching a hyperbola problem. Here we are just asked to sketch the hyperbola x minus 3 raised to the power of 2 divided by 9 minus y minus 1 all raised to the power of 2 divided by 4 equals 1. And this is sketch this hyperbola. So in trying to sketch this hyperbola, you need to know the features of the hyperbola. You know, from the standard formula you are given, which is x minus h all squared equals a squared minus y minus k all squared all over b squared equals 1. So we need to find these features h, a, k, b. We need to be able to find the values of those variables. So that will make it easy for us to sketch the hyperbola. Okay, so what is a? A here squared is given as 9, which implies a equals plus or minus 3. So in that case, plus or minus 3, this is, what does a represent in the graph? What does it represent? A represents the vertices of the hyperbola. So now we have the vertices are minus 3, 0, and 3, 0. Because the hyperbola is open on two sides, on the left and the right, so that's why you have on the negative side, this is minus 3, 0, and on the positive side, it's minus 3, 0. So now we know what A is. Let's find what are h, what is minus 3 here and minus 1. These are simply the center. That represents the center of the graph. We explained this already in previous videos. So we have center of graph is 3, 1. Those ones, you just read them off from the equation. Yeah? And what is B? B is the conjugate vertices. So B here we have 4. We have B squared equals 4. B 4. Therefore B is plus or minus 2. We find the square root of 4 is plus or minus 2. So conjugate vertices. Minus 2, 0 and 2, 0. So we finish with that. Now let's find the foci of the hyperbola. You get that one from a formula that says c squared equals to a squared plus b squared. So c squared here is equals to a squared, which is 9, plus b squared, which is 4, and that gives you 13. So c squared equals 13. Therefore, c equals the square root of 13. What is the square root of 13? Let me use my calculator. Root 13, 3.6. So you get plus or minus, sorry. 3.6. So the foci .6 comma 0 minus 3.6 comma 0 and 3.6 comma 0. In pairs, isn't it? Because you have got the left hand branch of the hyperbola. So now we've got all the features of the hyperbola. What is left now is to plot it. So let's try and sketch it. This is our x-axis, y-axis. We are not going that far, just 3. So we are told the center. This is y, this is x. If we put 1 here, 2, 3, the y is 1, we don't need to go as far as that. So put here 1 and 2, minus 1, minus 2. And here is 1, 2, 3. 1, 2, 3. Here again we have minus 1, minus 2, minus 3. Minus 1, minus 2, minus 3. Yeah? So the center on the x is 3. And on the y is 1. It's minus here, so we'll go positive. If it was positive here, it will be minus. That's how it works out. So if x is 3, that is, we are looking at the center here at x comma 3. X center is 3 comma 1, so 3, 1. So where this and these two meet, so this is our center. Oh, then I've pushed this too much here. Anyway, I'll extend it. This is the center of the hyperbola. So this is our 0 comma 0 in the standard form of hyperbola. This is the center of the hyperbola, because this hyperbola is not centered at the origin. Instead, it's centered here. So now we got our vertices, minus 3, comma 0, and 3, comma 0. So first, let's look at minus 3, comma 0 vertices. So if this is the center, you count 1, 2, 3. You go left, because minus 3, you go left. So which means the other points will be here. And on the right hand side, you have 3. So now foci minus 3.6, comma 0 and 3.6, comma 0. I want to erase this one here. But now I need this space. X here. 4, 5, 6, 7. So from here we count 3 steps. 1, 2, 3, because it's minus 3, yeah? Minus 3, comma 0. And again from here, we count 3 steps towards the right. 1, 2, 3. So our other point would be here. So these are our vertices. Yeah? So what we need to do now, we have, this is our vertex here. Our co-vertices to be minus 2, 0 and plus 2, 0. So again, you count 1, 2, so it's going to be here. And from here again, you count 1, 2, so it's going to be here. So all that you need, just draw straight lines, and then where they intersect, this is our center here. Where these lines meet with these points, draw vertical lines. Already your vertical line is here. So let me change the color of this thing. So you now have a rectangular hyperbola this way, and it goes through the value of 6 and here. Correct? This value is right here. And this one. These are our vertices. So you now draw a line, perpendicular lines, that passes through the center and to the diagonals. It's not that accurate, so I'm sorry about that. So like this, you draw another one, passes through the center like this. These diagonals can extend because they are at infinity. These are your asymptotes. Yeah? So then it's done. Once you are able to draw this rectangular hyperbola here from the features of the equation you are given, hyperbola equation you are given, then problem is done. Now the center, this is your vertex. So the curve starts here. That is the maximum turning point of the graph. It goes like this, and again it goes like this. They never meet. No, keep going. Again here, it goes like this. Here it goes like this. And your foci, which was minus 3.6, you know, this is, it was, if you add it to here, so 1, 2, 3, no, 1, 2, 3, so 3.6 will be somewhere around here. This is your focus. And 3.6 again will be somewhere around here. These are your foci. So this is your graph. You've plotted it. This is it. So next, the next topic we are going to move on to is called parametric equations. Just an introduction today. Parametric equations. Because when you are using these conic sections, parameterization becomes very, very important. It is widely used in the field of science, engineering, all these technological advances. And what does that mean, parametric equations? Parametric equations are used to represent curves and surfaces so that their behavior can be better observed and studied. That's why we use parameters in equations. Say, for example, you have a function. We don't know what the function yet. That says x equals 3t and y equals 9t squared. So how many variables do we have here? We have x, t, y. So it's 3 variables. Actually, you can have two variables, like y equals x squared plus 2. For example, this is quadratic equation, yeah? And then they will ask you, this is in the Cartesian coordinates. They will now ask you to introduce parameters in this equation. As we have explained, parametric equation, really, this idea of parameterization is very, very important. It helps a lot, especially in the field of astronomy, or all these engineers that launch satellites and all these kind of things. They use parametric equation to be able to locate whatever machines they are sending up there, so that at any point in time they know exactly where that object is. And sometimes you can hear in the news when they say there is a comet coming close to the earth, and at so particular time it will be this particular location. It's all parametric equations they use, because they use it with respect to time. That will be able to locate whatever object is in space at a precise location at a precise time. So you are given like this: y equals x squared plus 2. This is in the Cartesian form, and they ask you to introduce a parameter. So now you have two unknowns here. Introducing a parameter like time will make this equation to have 3 parameters. When you introduce time, t, then it will now have 3 parameters, 3 variables, x, y, and t. And what does that do to the equation? That means if this graph, plot it like this graph is going to look somehow. It's too, let me remove this to make it simple. It will be something like this. This is your y and this is your x. So at this point here, any point in the graph, it will have a coordinates of x and y. This coordinate here will be different from this coordinate here. This is x1, y1. This one here, the x5, y5. At any point on this graph, it will have an x and y coordinate. So if that is the case, now instead of you using coordinate finding what is x, what is y, by the use of parameters, you'll be able to know at what time would this point be at this particular location. If this was p, At what time will P be at this particular location? At what time will X be at this particular location? So that is what parameterization does for us. Very helpful. See that? This is just an example. Now we have this. We have this equation already given there. Y equals X equals 3t, Y equals 9t. The question says find the Cartesian equation of the curve. Equation of the curve in the form y equals f of x. So how do you go about it? So what do you do here? Now you want to eliminate t for you to transform these functions into a Cartesian coordinate. That is, you reduce the number of unknowns. We have 3, now you want to reduce them to 2. That is what is the main aspect of this parameterization. When you have complex functions like this with so many variables, you can be able to reduce them. So how do you reduce these ones? You have here x equals 3t. So this will give you t, make t as the subject of the formula. You now have x all over 3 equals t. Yeah? X all over 3 equals t. Now put this x all over 3 equals t. You have y equals 9t squared. If you now substitute for t in this equation, you have y equals 9t squared. But what is t squared? What is t? T is x all over 3 squared. Yeah? So this one you have 9 equals x squared. Sorry, y equals 9x squared all over 9 all over 9. Because when you square 3, you get 9. This is x squared. So the 9s cancel. You now have x squared. So you now have y equals x squared. So this is what the equation I've reduced to. So this one, we just done that. This is a parabola. Thanks for watching.
Thank you very much.